How are you doing today?
Good, how are you?
Good. Right, looks like we got some interesting stuff here.
Yeah, this stuff's fun.
We don't see this kind of stuff very often. Question number 2. It says use the intersection or root method.
Yeah.
Now, when I'm comparing a trig function to a polynomial function like number 2,
Yeah.
then the only way I know how to solve that is by graphing it. Graphing that as one equation, graphing that as another. You have the TI-84, correct?
No, TI Inspire.
Well, we'll have to do it on the TI-84. Are you familiar with the TI-84 at all?
Yeah, I've used it, but I'm more experienced on the other one because that's what I have.
Unfortunately, I don't have a virtual Inspire. I do have a virtual TI-84. So
That's fine.
I think you'll get the idea. The first equation is 2 cosine x. So I'm going to let y1 equal 2 cosine x, end paren, enter. And I'm going to let y2 equal the other side of the equation, which is x squared minus 1. X squared, x squared minus 1. Okay?
Yeah. Yep.
Now I'm going to graph both of them, and I'm going to find their intersection. And just like all equations, their intersection occurs wherever x makes them equal.
All right.
So I hit the graph button.
That doesn't look right.
Sure does not. We've got the parabola. That's x squared minus 1. But the first one does not look like 2 cosine x. So let's see what's... 2 cosine x, x squared minus 1. Well, let's see what's wrong here. If I clear that, and I clear that, and I go back, hold on. And I type cosine of x. Let's see what that graph looks like. What's going on here? I don't know what mode I'm in. I'm in degree mode. I may have to be in radian mode. Let's try it now.
That's weird.
Well, not really. one of the major differences between degree mode and radian mode is that radian is a number. Degrees are not. Degrees are a part of a circle. In other words, 1 degree is 101 over 360 of a circle, whereas a radian is an absolute number. So if I want to plot both functions, then I've got to make sure I'm in radians. So this is x squared, what was it, minus 1?
Yeah.
Now if I graph both of them, I can see where the intersection occurs. Now, on your Inspire, I wish I had a virtual Inspire. I'm going to have to search the internet and see if they've got one available. This TI-84, you've never worked with the TI-84?
I mean, in 8th grade we did, but then they gave us our Inspires, and then we're like, oh, this is old technology. We don't.
Yeah, well, you're right. The Inspire is much, much better than the TI-84. It's just that I can't show you how to find the intersection on the Inspire. But what we're looking for is that point there or that point there.
Yeah.
Okay. If I hit calc, which is that, gives me a choice of options, and if I want to choose the intersection, I'll choose that one. And now I have to make sure that the first curve is to the left of my intersection point, which it is. So I hit enter. Second curve, I'm okay on. I hit enter. Not going to make a guess, so I hit enter. And it gives me the intersection of that point right there, which is minus 1.17 on the x-axis and 0.384 on the y-axis. Okay? If I wanted to find the intersection of that point, I would hit second calc, choose intersection, make sure my first curve was somewhere near my intersection point. See how it's moving. Okay, I'll take that. Second curve's already there. I'm going to take that. I'm not going to guess. And it's going to tell me my second point is plus 1.17, 0.384. And these two things look very symmetrical. They are symmetrical. They should be symmetrical. So my y-axis should be the same for both intersection points. And my x-axis should be, in other words, that should be negative 1.17. That should be positive 1.17.
Yeah.
But that's basically the way we're going to solve these problems. Even if it's on your Inspire, we're going to do it that way.
Okay.
In other words, there's no real way to algebraically solve these.
All right, that makes sense.
I guess.
You can, but it just would take way longer than plugging in.
If I tried to solve the first one by an algebraic solution, I would have 2 cosine x plus 1 equals x squared. Take the square root of both sides, and I get problem is that I still don't have a way to come up with those numbers as to where those two intersect. And the problem is that this is a polynomial and this is a trig function. So it's very difficult. I mean, what are we going to use?
Nothing.
I don't know how to solve that, to be honest with you. The only way I know how to solve that is with a calculator. And you'll notice the calculator did give us two values, which was a plus and a minus.
Yeah.
So I'm going to use that. That's the only method I'm going to use for question number 2. I don't know any other method to use. For question number 3, natural log of the quantity x plus 2 plus 1 equals the integer function of x. This is another problem where I'm relating two different kinds of functions. This is a natural log function, which is similar to an exponential. In other words, that's similar to e to the x. And integer of x, what does int of x mean? Is it greatest integer?
She didn't really explain what that meant. She's kind of, because on the Inspire, that's what, if you go into the little booklet.
Type it in as int of x.
Yeah.
All right.
So well, I'm not really sure what that is.
You're going to do the same thing here as we did on number 2. This is going to be your first function, the left side of the equation. That's going to be your second function, the right side of the equation. And you're going to trace your cursor to the intersection point and find out where they intersect. Now, 4 looks a little different because 4, we're looking at a bunch of polynomial equations. Maybe I can solve 4 without a calculator.
Couldn't you just take the top one and just put that, and so it'd be x equals parentheses x cubed to squared and minus 2?
Correct. It's exactly what you can do. And then you end up with x equal x, what's this term?
To the 6th.
Correct. Minus 2. Now you could put that into your calculator and find the zeros of that. In other words, how would we put that into our calculator? We would have to put it in as x to the 6th minus x minus 2. That's equal to 0. So as long as we put that function into our calculator and find the zeros, we're going to find the solution. Now, given that that is a polynomial of the 6th degree, we should have 6 solutions. If I put that into my virtual calculator as my y function, should cross the x-axis 6 times. And we just need to find each of those spots.
I'm pretty sure there's imaginary, though. Unless it's really far out.
Well, you're right. In other words, we know that there are 6 solutions to this, but we don't know that there are 6 real solutions. Oh, we just know there are 6 solutions. And so we might end up, if there were, say, 2 real and 4 imaginary, we might have something that looked like that. Those would be the real solutions. The imaginary solutions would not cross the x-axis. That's the thing about imaginary solutions, is they do not give you zeros. So the only thing we know about this is there's probably 6 solutions, and we'd have to actually graph it in order to see. Let me open up Wolfram Alpha, which is just, I mean, as long as we're not working on a TI-84 anyway, let's not do stuff on a TI-84. Let's do stuff on Wolfram Alpha. It's a better graphing calculator. So this was x to the 6th minus x minus 2. Is that what it was?
Yep.
Gives us the input, correct? And there's what it looks like. And you're absolutely right. There's a 0 at minus 10. There's a 0 somewhere there after 1. And that's it. We don't see any other zeros. So there must be 4 imaginary solutions, and there must be 2 real solutions. And if I go down here, here's my real solutions. I have x at minus 1.
They should have one more.
Oh, yeah. Oh, there's the second one. I was covering it up. And x of 1 point, some irrational number, 1.21486. And then here's the 4 complex solutions. I don't know of a better way to solve that either, other than you could use the intersection method here, but you don't need to. In other words, all you need to do is use substitution to turn it into one equation and graph it and find the zeros of that equation. So whenever you have similar type equations, in other words, a polynomial and a polynomial, that's a trig function and a polynomial, that's a natural log function and a different kind of function. But when we have polynomial, you can use substitution and graph it. You don't need to find intersection points, you can just find the zeros. Now, number 5. Number 5 is 2 equations and 2 unknowns, right?
Yeah.
So I might even be able to do this without a calculator. Let's see. I'm going to put both equations in standard format. So the first equation is going to be minus 6x plus 3y equals 13. You understand that?
Yep.
Second equation, I'm going to bring the 10x over. So I have minus 10x. I'm going to expand that, which is y squared plus 6y plus 9, multiplying it by 2. So it's 2y squared plus 12y plus 18. In other words, after I expand that. Is that cubed? Oh, it is cubed.
Yeah, it is cubed. So it's way more work.
Right, it's way more work. You hit it. We could still probably solve it, but it's going to be solving a cubic instead of a quadratic, and that's a lot harder to do. So what other technique can we do here?
Solve for y.
We could solve both equations for y, put them into the calculator, and find their intersection points. First equation solves for y pretty easily. Y equals 6x plus 13 divided by 3. So that's the first equation we want to put into the calculator. Second equation, we end up with y plus 3 cubed. And cubes are actually easier to work with than squares because they only give you one answer. They don't give you a plus and minus. So that's equal to 10x minus 5 divided by 2. You with me?
Yep.
Which means that y plus 3 equals the cube root of that. Which means y equals the cube root of that minus 3. So there's my 1y that I'm going to put into my calculator. There's the second y that I'm going to put into my calculator. Wherever the two shall meet, that's the intersection point.
Okay.
Okay? You don't have any problem finding the intersection points on your Inspire?
No, because there's a actual, like, when you just go into menu and then analyze graph,
right.
There is a intersection.
And you don't even have to go through the nonsense of trace. It tells you the intersection point immediately.
Yeah.
So yeah, the Inspire, I've got an Inspire. One thing I'm a little curious about here is why they have two different methods of solving this. That was the intersection method. That was the intersection method.
4 is kind of the root method.
I guess, yeah, you're right. 4 is kind of the root method. Although the problem with 4 is finding the roots of a sixth degree polynomial is not that easy.
Yeah.
I guess I could also use the intersection method here by letting y equal x cubed and letting this y equal the square root of x plus 2. Now wherever those two y's intersect, that's the solution. Number 6. Let's just set it up as a third degree polynomial and find the zeros. How do I do that? Am I going to use the calculator, the Inspire, to solve for number 6?
Wouldn't you just plug both of them in to the graph?
Guess you could do that. In other words, the left side of the equation would be the first function. The right side of the equation would be the second function. And you would look for the intersection.
Yeah.
But another way to do it, using the root method, would, well, let's bring the left side of the equation to the right side, leaving 0 behind. And now we
Wouldn't it be a little easier to go the other way so you get rid of the negatives?
You're correct, but I'm going to give you a quick and simple method of doing that. Notice that is all I have to do now is divide both sides by -1. Turn that positive, that positive, that positive, and this negative. That's a 0.5. Now, if you put that cubic And you can put it in as y equals. Doesn't have to be 0 equals. The thing is if you put that in as y equals, it will give you the zeros. You can pull up your menu option and say, give me the zeros, and it'll tell them to you. And whatever the zeros of that function are, in other words, that function is going to look something like this. There's usually 3 zeros. There's one, there's another, there's the third.
Yeah.
So on this one here, you can use either the intersection or the root method. I'm not sure one is more easier than the other. 7. Now, notice 7 is strange in that that's not an algebraic expression. That is an exponential expression. You cannot use algebra to solve an exponential expression. We do not have any algebra that lets us solve this. But if I put that into my equation as function 1 and that as function 2, you will see that there is an intersection point which you can find. I don't believe there's any way to use like a root method for this. I could bring everything over to the same side, but I still have the problem of I'm dealing with an algebraic and an exponential function. You cannot use algebra to solve exponential functions. In other words, if I told you 2 to the x equals 5, there's no way to use algebra to solve that.
Yep, you have to use logs.
You have to use logs. You'd have to use log base 2 or natural log or something. But you can't use algebra. So it's really important to recognize that when the variable is in the exponent, it is not an algebraic expression. When the variable is on the algebra line, then it is. But if you have one equal to the other, you've got to use a calculator to solve that. All right. That's a half hour. Do you have any problems with these bottom two at all?
No, that's all playing into your calculator. I was more having problems just like what to do on like
In other words, this
4
one,
and 5.
this one you put into your calculator and you find the minimum from your menu. This one, you just substitute minus 15 for x.
Yeah, or we just use the trace function on the calculator.
Okay. However, conceptually, on number 9, it's pretty important to know that if f of x equals that, what is f of minus 15? It means you substitute whatever's in the parentheses for x.
Yeah.
Because as you move into calculus, that's a very important concept. Because I might say, what is f of x plus h? In which case, we have to plug in x plus h in for x. And then figure out what that function is. What is f of x plus h? So it's important you understand that whatever's in the parentheses, you plug in for x. In this case, it's a number, so it's relatively easy. But it could be a variable. It could be what is f of x plus 3, in which case we plug in x plus 3 wherever we see x. All right. That's good stuff. You're getting some harder stuff.
Yeah, now we're actually getting into the pre-calc stuff.
Yeah, this is the hardest stuff I've seen you get. Although it's not really that hard. It'd be really hard if you didn't have a calculator. But as long as you have a calculator, it's not that hard.
Yes.
So, all right. Mitch, I will talk to you next Wednesday.
All right.
Have a good one. Bye-bye.